Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. I talked a bit about why I started this podcast last week. Engineering failures are not talked about. They're embarrassing, uncomfortable, and often costly. No one wants to admit they made a mistake. But engineers are not infallible, and any engineer who tells you that their designs never have any mistakes, they're lying. We as an engineering community have to talk about failures. We have to talk about the ugly. How can we expect to stop history from repeating itself if we're too scared to talk about it? How can we expect to learn if we don't uncover the ugly of these failures? That is what I hope to accomplish. Make no mistake, I'm not trying to shame anyone here. I don't believe in cancel culture, but I hope that by sharing these stories, we can make a difference. And with that said, we made it to holiday season! Woohoo! The last month or two have been very busy for me, and while I'm thankful to be working and healthy, boy, do I ever need a nap. There's always this big push at work from contractors and developers to get occupancy certificates before everything shuts down for the holidays, so my Decembers are usually stressful. But then I get a bit of much needed time off, which I'm very much looking forward to after this crazy year. I can't believe it's only been 9 months since COVID changed our lives in Canada. This year has been the longest decade ever. But vaccines are arriving and have started being distributed to healthcare workers. And while I can start to see a light at the end of this tunnel, it's not going to be easy to get there. We still have a lot of new and active cases in Alberta that need to get under control, and we're in lockdown until mid-January at the earliest, which I am fortunate enough to be okay with. Whatever we have to do to keep people safe and healthy is fine with me. But I know there are others who are not as lucky, and I hope that they're doing okay. So whether you celebrate Christmas, Hanukkah, Kwanzaa, or none of the above, I hope you're happy and healthy this holiday season. And if you don't get to be with your loved ones in person this year, I'm sorry. If you're feeling lonely or bored this holiday season, reach out to me. We can nerd out on engineering things or chat about whatever else catches your fancy. I'd love to hear from you. My Twitter handle is @failurology, or if you want to email me, you can send it to thefailurologypodcast@gmail.com. I'll put both of these in the show notes of this episode. Today's episode is a very iconic Canadian failure, the Quebec Bridge collapse. This is the first Canadian failure I've covered. Not only did the bridge collapse twice, the failure also jump-started the creation of engineering regulations and ethics commissions and led to the iron ring tradition of Canadian engineers. I'm going to dig into all of that very soon, but first, the news. This week in engineering news, a 3-story apartment building in Germany made with the help of a 3D printer. The apartment building is 3 floors and about 375 square meters, containing 5 apartments. The German formwork and scaffolding company Perry is using a BOD2 printer, which they claim to be the fastest available 3D construction printer. This printer can print a 1 square meter facade in 5 minutes. It also moves throughout its frame to any part of the project without needing to be recalibrated. The project consists of printed concrete for all the walls. A good portion of the interior walls are curved, and the 3D printer traces the wall outline over and over, adding a layer each time. And then there's a gap in the walls as well, which I assume will be filled with insulation for thermal or acoustic reasons. The floor and other things like pipes, ductwork, and electrical can't be printed in, so they'll have to be installed in a traditional fashion. The project's expected to finish in March or April of 2021. I knew this day would come eventually, and it's pretty exciting and just the tip of the iceberg. Other teams have built houses and single-story structures, but this is the first multi-story apartment building that I've been able to find. There are several videos online about the project, and I recommend checking them out. Watching the printer is oddly satisfying, kind of like watching power washing videos. If you want to read more on this 3D printed apartment project, check out the link in the show notes. Today's engineering failure is the Quebec Bridge, or Pont de Quebec collapse, the bridge that collapsed twice. The Quebec Bridge collapse is said to be Canada's worst engineering disaster. Before I get into it, I want to take a second to mention that while I am Canadian, my French is not very good. Je parle un petit peu français. I hope I get most of the French pronunciation right, so please wish me luck. The Quebec Bridge connects Quebec City and Lévis across the St. Lawrence River. At the narrowest section, the river is 3.2 kilometers wide, 59 meters deep in the middle, with an average water velocity of 13 to 14 kilometers per hour and a tide range of 5 meters. In the winter, ice used to get stuck in the narrow and pile up to about 15 meters high. Before the bridge, boats were used to cross in the summer, and in the winter, they built an ice bridge. There was no crossing in spring or fall when the ice was too thick to cross by boat or too thin to cross by ice road. Montreal built the Victoria Bridge in 1859, and Quebec City, wanting to remain competitive in trade, needed a year-round crossing. Quebec City residents had been asking for the bridge since as early as 1852. A site was chosen where the river narrows roughly 10 kilometers upstream from downtown Quebec City. But then nothing really happened for several years. But in 1898, a design competition was held, and the Phoenix Bridge Company's design was selected. Their design was for a cantilever bridge, with 488 meters between supporting piers. I promise that point is important. A cantilever bridge is a bridge with two piers on either side of the river crossing, and then the bridge deck spans across between those two piers. They call it a cantilever bridge because the bridge decks are cantilevered or supported out from the piers with nothing in the middle to support the span. These types of bridges are common when there is significant river traffic flowing under the bridge, as any piers in the middle would restrict access and limit ship sizes that could pass through. Shortly after 5:30 p.m. on August 29, 1907, during construction, the southern cantilever span, which at the time was 180 meters over the river, twisted and fell 46 meters into the river below. 75 workers, including many of the Kahnawake tribe, were killed. Reportedly, 86 people were on the span at the end of the workday. There were 11 survivors. Among those who perished were Benjamin A. Yenser, the general foreman of erection, who had worked for the bridge building company, and Arthur Burks, resident engineer of erection. The crash was heard in Quebec. It was so loud that locals thought it was an earthquake. The cause was ultimately determined to be a faulty design and inadequate engineering supervision. There were 4 parties involved in the initial construction of the bridge. These are the major players. There was the Government of Canada, who funded the bridge, the Quebec Bridge and Railway Company, who was responsible for completing the structure. Edward Hoare was the chief engineer. Theodore Cooper of New York was the consulting engineer hired to design the bridge. He was the full technical authority. Today we would have referred to Cooper as the engineer of record or the signing stamping engineer. And with the Quebec Bridge and Rail Company, there was also Norman McClure, the inspector of erection. He was a 1904 Princeton grad who was technical, and he reported to Hoare, the chief engineer, on matters of monthly estimates, and he reported to Cooper, the design consultant engineer, on matters of construction. The Phoenix Bridge Company, out of Phoenixville, Pennsylvania, designed and constructed the superstructure. The chief engineer, Mr. Deans, was an experienced bridge builder, but he acted as a chief business manager. He was more concerned with the business aspects of the project rather than the engineering. And the design engineer, Mr. Zlapka, was a German-educated engineer with 27 years of experience on similar projects. Under Cooper, he was responsible for generating the design details. And then there was the Phoenix Iron Company, who fabricated the steel components. Don't worry, I'm going to reference these people while explaining the first collapse, so I'll remind you who they are as I go. Cooper was a consulting engineer out of New York hired to design the bridge concept put forth by the Phoenix Bridge Company. Cooper had designed the 2nd Avenue Bridge in New York City, which was an elevated train bridge from 1878 to 1942. After investigating the riverbed of the St. Lawrence, Cooper recommended the piers be closer to shore, increasing the span from 488 meters to 549 meters. See, I told you that part was important, because this is where things started to go wrong. The bridge design included anchor arms on each end, support piers in the water, now 549 meters apart, and cantilevered spans of bridge deck from each pier. On the cantilevered spans, the bottom structural members were in compression and the top members were in tension, with members in a lattice pattern in between. Let's try an experiment, shall we? If you're driving, just imagine it. Hold your arm out to your side. You, yourself, your body are the support pier, and your arm is the bridge deck. Now imagine a downward force is being applied to your hand. As your hand moves down, the top of your arm is elongating, or in tension, and the bottom is shortening, or in compression. This is the same scenario as a cantilevered bridge span. The Quebec Bridge is the longest cantilever span in the world still to this day, and the deck sits about 46 meters above the river at high tide. The Quebec Bridge was inspired by the Forth Bridge in Scotland, built in 1890, just west of Edinburgh. The Forth Bridge has two 521-meter spans and remains the second longest cantilever bridge in the world. Construction for the Quebec Bridge began on October 2, 1900. There were several problems noticed during construction, but their importance was discovered too late. First, pre-drilled holes for sections that were supposed to bolt together didn't line up. This implies that additional stresses on members would have put them out of alignment, meaning they weren't where they were supposed to be. Today you can survey members to make sure they're in the right spot, but this was 1907. That technology didn't exist. Some ends of pieces of steel that had been joined together were bent, specifically on the lower chords of the south arm. Remember the arm exercise. These members were in compression. The bending was first noticed on June 15th and observed until the collapse on August 29th. Deans, the chief engineer for the Phoenix Bridge Company, insisted work continue. Remember that he was more focused on the business of the project, not the engineering. Deflection of the south arm lower chord members ranged from 1.5 to 57 meters across 15 different structural members. 1.5 millimeters may have been within tolerance or determined to be pre-existing conditions and didn't cause immediate alarm, but 57 millimeters of deflection certainly raised a red flag. The manufacturer had guaranteed that the members were straight when they left the yard. However, one member was dropped and bent while at a storage yard. All of the major structural members were tagged. The dropped one in particular was tagged A9L, which was a structural chord in the anchor arm, A, in the ninth panel, 9, on the left or west side of the bridge, L. It was believed to have been repaired, but later determined to be the triggering cause of the collapse. A9L went from 19 millimeters to 57 millimeters of deflection in 2 weeks. A9R, which is the same chord on the right or east side of the bridge, was bent in the same direction. Based on what we know, the bridge was still likely to collapse regardless of whether A9L was damaged. But as tragic as the collapse was, it was likely less destructive than if it had happened after the bridge was open to the public. Why can't these things happen in the middle of the night when no one is there? Several weeks before the collapse, Cooper, the consulting engineer who designed the bridge, was notified by McClure, the director of inspection for the Quebec Bridge and Railway Company, by letter of the bending issues on site and suggested corrective procedures. The members with the highest compression load were starting to buckle. But Cooper rejected the proposal, asking how the bends had occurred. He believed the cords were damaged during erection. When someone says there's a problem, you check your numbers. Even if you disagree with them, you double check anyways. A lot of engineers work in Excel or other software, which makes it easier to rerun formulas under different parameters with minimal time spent. The point of the story here is, when someone says there's a problem, you check your numbers. Letters went back and forth for 3 weeks between Cooper, McClure, and Deans, the chief engineer for the Phoenix Bridge Company, acting as a business manager. Cooper sought to understand how the steel was bent and rejected multiple explanations. Slapka, the design engineer for the Phoenix Bridge Company, stated he was certain the bend was put in the cord ribs at the shop, but he later admitted that he'd never actually seen the cords in question at the shop. 2 days before the collapse on August 27th, McClure, director of inspection for the Quebec Bridge and Railway Company, found additional bending of other cords in the truss work and measured the deflection. The erection of steel was suspended until Cooper, the consulting engineer, and the bridge company could evaluate the situation. McClure, the director of inspection, went to New York to discuss with Cooper, but unbeknownst to McClure, Hoare, the chief engineer for the Quebec Bridge and Railway Company, authorized the work on the bridge to resume. Upon discussing with McClure, Cooper wired Phoenixville, where the Phoenix Bridge Company was located, with the message, "Add no more load to the bridge till after due consideration of facts." McClure, thinking that work was still suspended, not realizing Hoare had resumed it, didn't urge direct contact with Quebec. Due to a telegraph strike, it's unclear if Cooper's telegram to Phoenixville was undelivered or unread. One article noted that Deans, the chief engineer for the Phoenix Bridge Company, read the wire and ignored it. Within hours of the collapse, a royal commission was established consisting of 3 investigators, Henry Holgate, John George Gale Carey, and John Galbraith. Their investigation came to the following conclusions. As far as the design itself, failure occurred from lower chords A9L and A9R in the anchor arm of the main pier, due to defective design. Remember that A9L was damaged in the seal yard and believed to be repaired, but the commission believed the members were undersized and failure would have occurred regardless. Cooper increased the allowable stresses on the compressive or lower members. He developed a formula to calculate allowable compressive stress, which was 3.3 to 8.7% higher than stresses in use today. The design was unsafe practice and questioned for being unusually high, but based on Cooper's reputation, the questioning didn't go very far. The design loads were underestimated. Stresses calculated by Zlapka, the Phoenix Bridge Company design engineer, using Cooper's, the consulting design engineer, estimate of total dead weight was from the start of the design process. But remember, the distance between the spans changed from 488 meters to 549 meters at the beginning of design, which impacted the dead weight, but the stresses were not recalculated. Assumptions have to be made to start the design. You can't start to build a bridge without at least a guess of how heavy it will be. But once you have a design, you have to go back and recalculate those loads. Cooper was aware of the underestimate of weight, but only after considerable material was fabricated and construction had begun. Cooper calculated an underestimate of 7 to 10%, which he believed was still within acceptable tolerance. Later analysis showed the underestimate to be about 20%. There was also minimal budget for testing, and once said budget was available, Cooper said it was too late. And lastly, on the design issues, the top and bottom chords were designed as curve members, which resulted in difficult fabrication and reduced bulking capacity. It also resulted in increased secondary stresses on members, which are more dangerous in tension than compression. On top of the design issues, the commission also found several personnel problems. The Quebec Bridge and Railway Company took 2 years and $500,000 to prepare specifications, but then expected engineering companies to prepare detailed competitive bids for free in 4 months. Cooper, the consulting engineer who designed the bridge, assumed a great responsibility for inadequate salary, and then there were no provisions in that salary for him to hire staff to assist him. The pay was so small, he wasn't able to outsource any work to junior staff, leaving him little time to investigate the data and theories used in the design and allowed errors to go unnoticed. His reputation gave false security that no issues would arise, and therefore he was scrutinized less. He even rejected to an independent engineer checking his work. The unwavering trust in Cooper is interesting because he was unable to visit the site in the 2 final years of the project due to poor health. Distance from site and minimal tools also made communication difficult. This wouldn't be permitted today. Design engineers are legally required to review their designs during construction. If they can't review in person, they have to appoint someone to do so on their behalf. This is what I do, except for plumbing and HVAC systems. No clear order of command existed on the project. It was assumed that authority rested with Cooper, even though there was no one on site qualified to oversee construction. During construction, engineers wasted time arguing over the cause of the deformation and whose fault it was that the bridge collapsed. Some workers even refused to show up because of the deformation. Engineers must be open-minded to ideas and hands-on experience of laborers and contractors. Not only are they down there in the trenches, spending hours a day looking at small details of the bridge construction, they've probably done enough of these to know when something looks off. But Cooper wasn't the only one criticized. The investigation found that appointing Hoare as the chief engineer for the Quebec Bridge and Railway Company was a mistake, and he was not believed to be technically competent to control the work. Deans, the chief engineer for the bridge company, was believed to be lacking in caution and failed to appreciate emergencies that arose. And Slapka, the design engineer for the Phoenix Bridge Company, criticized Cooper for making the bottom chords curved for artistic reasons and for not visiting Phoenixville during fabrication. The Royal Commission's investigation found that loss of life could have been prevented with better judgment and that the failure was caused by design flaws and not manufacturing. After the investigation and a 2-year removal of the collapsed portion, the Government of Canada, realizing the bridge was a vital transportation route, decided to rebuild. A 3-person board of engineers was established to prepare plans and specifications and supervise the work. This time, the board's duties and powers were clearly defined. There were also some significant design changes. The original bridge was intended to be constructed in place, cantilevering out the bridge decks from each side until they met in the middle. But the redesigned construction spanned the bridge decks partway, with the middle span built on shore and floated out to be raised into position. The cross-sectional area of original compression members was half a square meter versus 1.25 square meters with the new bridge, and the new bridge weighed 2.5 times as much as the initial design, which the design properly calculated and accounted for. The new design also revised the bridge to wider piers and straight lower chords. The St. Lawrence Bridge Company of Montreal was hired to erect the bridge, but on September 11, 1916, at 11 a.m., while lifting the center span into place little more than 7 meters above the water, a sharp crack was heard and the span slid off its four corner supports into the river next to the wreckage from the original collapse. 13 workers were killed and 14 more were injured. This was just a few days past the 9-year anniversary of the first collapse, and this section that fell is still there today. An investigation found no design flaw. There was a material failure in one of the 4 bearing castings that temporarily supported the span while it was transported and hoisted into place. The St. Lawrence Bridge Company took responsibility. A second span was constructed, and design of the support bearing was revised. The new span was lifted into place over 3 days in August 1917. The bridge was completed later that year and opened to traffic in 1918. The official opening was December 3, 1919. Ironically, Cooper died 2 days later. The final cost of the bridge was $22 million, which is equivalent to over $330 million today. Here's a fun fact that really has nothing to do with the collapse, but I thought was interesting. The bridge was officially opened by the Prince of Wales, Edward VIII, who is Queen Elizabeth's uncle. Edward VIII abdicated the throne to marry an American divorcee, allowing his brother Albert, Queen Elizabeth's dad, to ascend to the throne. Over the years, the bridge has offered passage to road, rail, and pedestrian traffic. The bridge had 2 rail lanes until 1949, then reduced to 1, and even carried a streetcar line at one time. The first road lane opened in 1929, the second lane in 1949, and a third in 1993. The bridge has 1 pedestrian walkway. It originally had 2. The bridge has been owned by the Canadian National Railway since 1993. I want to share a list of lessons learned from the Canadian Professional Engineering and Geoscience Practice and Ethics textbook written by Gordon C. Andrews. Provide adequate funds for large-scale projects. Hire capable and competent professionals. Define clearly the duties, authority, and responsibility of personnel. Discuss design decisions and technical problems openly. Review details. Monitor the work on site adequately. Ensure that communication is rapid and accurate, and provide adequate support staff and pay the professional people appropriately. Following this collapse came the forming of the American Institute of Steel Construction in 1921 and the American Association of State Highway and Transportation Officials in 1914, both as a means to fund research which was too difficult and expensive for manufacturers to do themselves. As I mentioned at the top of the episode, the collapse jump-started the creation of engineering regulations and ethics commissions, and it also led to the Iron Ring tradition to symbolize humility and fallibility of engineers. Today, Engineers Canada defines the 5 duties of an engineer. A duty to public safety, to put public safety and health above all else. A duty to the client, do not disclose project-specific information to the public unless there is a safety risk, and present consequences if professional decisions are overruled. A duty to the employer, no moonlighting or accepting money to shortcut designs. A duty to the profession, self-governance, and reporting unprofessional conduct. And lastly, a duty to self, adequate compensation, and continuing professional development. Thanks for listening to this episode on the Quebec Bridge collapse. I hope you enjoyed it and found it as interesting as I did. Please check out the podcast page, link in show notes, for photos from this week's episode. And if you want to chat with me, my Twitter handle is @failurology, or you can email me at thefailurologypodcast@gmail.com. Thanks everyone for listening. If you're enjoying what you're hearing, please rate, review, and subscribe to the podcast so more people can find it. And don't forget to tune in next week to hear about the Hartford Arena roof collapse, the first computer-aided design failure. But more on that next week. Bye everyone. Talk soon.